So, model-driven telemetry is a fancy term and kind of an intimidating term, isn't it? I mean, immediately when I heard model-driven telemetry, I was like, that sounds like it's going to be really hard to implement. My goal right now is to break this down for you into plain English, what model-driven telemetry really is under the hood, and then we'll wrap up by talking about how we can deploy model-driven telemetry within our environment. Ultimately, what this is going to do is it's going to make our ability to monitor and troubleshoot our environment a lot better. Let's draw it up. First, what I want you to do is I want you to think about how we've been interacting with network devices up until this point. This will be our computer here. And when we've wanted to interact with, say, this switch right here, we've connected into this device and pulled data out of it. Maybe we're using NetConf and we've used the get RPC or the get config RPC, or maybe we've used RESTCONF and we've used the HTTP get method. Ultimately, it's on us to initiate the connection into this network device and then pull data out. Then once we've got that data, we make decisions on what to do. Maybe we then try to get configuration data and we'll make a decision on if we want to change the configuration after that. The point is we're connecting in and we're pulling data out of the device and back into our computer. The issue with that is we're reactive. We're waiting for something to happen on our network device that triggers us to connect into the device and pull data out. What if we wanted to be more proactive? I mean, we are talking about trying to get rid of SNMP, and SNMP polling made this a lot better. Let me redraw this for you for a second, and we'll talk about what model-driven telemetry really means. With model-driven telemetry, what we're actually saying is this network device can be configured to push specific data out on an interval or upon an important change. So rather than us connecting to the device, requesting data, and pulling it out, we can tell this device, push specific data out. And that immediately brings up one of the biggest distinctions that there is when does this network device push it out? This could be on a specific interval. In Cisco documentation, you'll see this listed as the cadence or the period, or we can tell it to push this data out on change. So what's an example of something that you would want on an interval versus something that you would want on a change? Something that I would want on an interval may be something like monitoring CPU load versus monitoring CDP neighbors. I may want to watch my CPU load over time so it looks like a chart that's doing something like this, where the y-axis represents the CPU load and the x-axis represents the time. Whereas with the on-change notification, I may want to be notified when the CDP neighbor status changes. Using this push model of data, we can specify which item we want to monitor, in this case CPU usage or CDP neighbors, and then how often we want to be notified about this. Ultimately, the idea is that we can now get insights into our entire network or all of our network devices without us having to request this information. The network devices can then push all of this information out to a computer where we can then move the data into a log analytics platform. One of the more popular log analytics platform is called the ELK stack. This stands for Elasticsearch, Logstash, and Kibana. The components for this are basically the Logstash stores or stashes our log information that's getting pushed in. Elasticsearch helps us narrow down and parse the data out, and Kibana is what graphs it out. There are other solutions that, quite frankly, are much easier to deploy, but for exam environments, you're going to want to know about the ELK stack. Personally, I would much rather use something like PowerBI streaming datasets. For the low cost of a PowerBI Pro subscription, we can now stream the data straight to Azure Cloud resources that are hosted on PowerBI and get real-time updates to our dashboards. That's just me personally. Well, this is all well and good, but how does it actually work? What is it really doing under the hood? Let's clear the screen and talk about this in a little more depth. Model-driven telemetry uses a classic development architecture called pub-sub, or for publisher and subscriber. When we're firing up our computer and we're wanting this data to be sent to us, what we're telling it to do under the hood is we want to subscribe to a network event that's going to be published out. The network device in this case is the publisher, and our computer is the subscriber. So we tell the network device that, hey, we want you to publish details, and we'll subscribe to those details. And what those details are under the hood is a specific Yang data model. Now it's time to actually look up here in the XML and you can see what's happening. In this XML, we're using NetConf, and we actually send in a new RPC that we haven't talked about yet called the Establish Subscription RPC. And what is it that we're specifically subscribing to? What is it that we want pushed out to us? Well, that's what's brought about when we talk about the XPath filter. This is the Yang model that we're going to be subscribing to. And in this case, this example is actually subscribing to active subscriptions. So anytime a new NetConf device subscribes to some model on this network device, this subscription will alert us that there's a new subscription. And how do we know if this is an on-change subscription or if this is a cadence subscription is right here. The tag that's being used is period. And this period is set to 1000, which is actually in centiseconds. So in this case, every 10 seconds, this network device is going to push any changes to the subscriptions that are being established. So the workflow is going to be that our computer establishes a NetConf session to this switch and then enables a subscription. And as long as that NetConf session stays active and open and connected, this network device every 10 seconds will push subscription changes back to our computer. The moment the NetConf session is disconnected or closed, the subscription ends. So while our computer is gathering data or listening for these push notifications, it can then forward that data onto an ELK stack, or like I said earlier, the PowerBI streaming data set. And with beautiful charts, we'll be able to see spikes in CPU activities or changes in OSPF neighbor adjacencies. What you should really be imagining is a gigantic 110-inch TV with all of these beautiful charts showing you what's going on with your network devices, and any alerts should be flashing red. So that's been understanding what model-driven telemetry really is under the hood. In the next nugget, we're going to roll up our sleeves and see if we can get a model-driven telemetry subscription going with the DevNet Sandbox. I hope this has been informative for you, and I'd like to thank you for viewing.